This video will teach you what you need to know about the normal force. Normal means perpendicular, as we've said before. It's specifically used for when you don't have two lines that are perpendicular, but perhaps you have, say, the marker perpendicular to the surface of the board, or you have a straight line perpendicular to a curve. The cause is, as we learned in ninth grade, that a compressed surface pushes back, just like a bed. If you lie in a bed and compress it, it pushes back, but you can see that compression. When a brick is on a floor, you don't see the compression of the floor, but it's the same reason. And that can help us understand the reason that the normal force can change and have different values for the same two surfaces, and also the reason for its direction. You draw the normal force in your force diagram whenever your object of interest touches a flat surface, and the direction will always be away from that surface and into the object, pushing back on the object, perpendicular or normal to that pushing surface that the object is touching. All right, this was not in the rules for forces. Those did not deal with strength. So here's the rule for the strength of the normal force. Unlike the gravity force, or the spring force, or the friction force, or the electric force, there's no formula for this force. It has no formula into which you plug numbers. Instead, this is the force that makes up the difference. This is the force that does whatever it takes to make the Newton's second law balance and be correct as an equation. So in this simple equation here, in this simple example here, let's say that all forces are pointing upward. So all the numbers are positive. And we have three forces involved. So this is the sigma F, the sum of the forces part of Newton's second law. And then the mass of the object of interest is 3 kilograms, and its acceleration is 7 meters per second squared upward. So you plug all these in, and you can figure out what the normal force would be. And of course, in this case, it's what? It's 10 newtons. All right, now we're going to do several examples that are force diagrams, not equations like this, but force diagrams. But the same idea applies. The value of the normal force is whatever it takes to make Newton's second law correct, to make Newton's second law balance as an equation. Here's the first example, very simple 4 kilogram brick sitting still, acceleration equals 0 on a floor. Draw a force diagram for it. Gravity force points down. The default is it's on Earth, so you multiply the mass by 10 and you get 40 newtons. And now if that were the only force, Newton's second law would not balance. The equation would not work. The forces would not add up to 4 times 0, which is 0. So that tells you the normal force, which we know has to point upward because it's got to be away from that flat surface. Not upward because it's balancing gravity. Upward because this flat floor is being compressed and it's pushing back. So the direction and the name of this force are given just from the picture. But since A equals 0, we can also figure out the number. That has to be 40 newtons. So that when you add positive 40 plus negative 40, you get 0, and that equals MA. All right, second case. Everything's the same except we have an additional downward force from a person pushing down with 30 newtons. So if we draw a force diagram for this diagram, we draw the gravity force, which we can quickly figure out is 40, the given push force, which is 30, and we draw the normal force, which must point upward because this brick is touching a flat surface and it points away from the compressed flat surface. That's why the normal force points upward, not because of what's going on here. All right, but we can figure out the number, the strength of the normal force because of what's going on here. You take this and you combine it with this, and you get that the normal force must be 70 newtons. If it did not say A equals 0, if A might be some other number, this isn't necessarily 70. There's no rule that this always has to balance everything else out and cancel it to make a total of 0. It's only equal to these because A is 0 in this example. Here is a brick being held against a ceiling by a person's hand pushing upward. FP equals 100 newtons. All right, so let's draw a force diagram for this brick. I draw the gravity force first because I'm likely to forget it. the upward force of push is given as 100 newtons, and it can help you to draw the arrows shorter or longer depending on their values. So I drew the 100 Newton arrow longer than the 40. It's never required, but it can help you feel if something is missing. Okay, are there any other forces we should draw? No springs, right? It's not sliding, that's not given, but it's touching a flat surface. This brick is touching a flat surface, which is the ceiling, and the normal force from a ceiling has to point down because the ceiling's being compressed and it pushes back. So in this case, the normal force has to point downward. All right, can we figure out its strength, its numerical value? Yes, I forgot to add one thing. So this will be in your video, but I would have to put this on a test. It's implied here that A equals 0. I better write that A equals 0. That's a motionless brick remaining motionless. A equals 0. All right, and once we know this, now we can fill in the missing value of the force. That has to be 60 newtons. So that the downs balance the up and create a total force on this, a net force of 0, so that 4 times 0 is 0, and the net force is 0, and Newton's second law as an equation balances. All right, here's our final example. You see in this one, the acceleration is no longer 0. In this example, the acceleration is 5 meters per second squared upward. So that's going to change things. So first, let's draw a force diagram. Okay, is that it? Is that all? No, this is a brick on the floor of an elevator. So it's on a floor, it's touching a flat surface. So that means there's a normal force pointing away from that flat surface upward. But just looking at this, I can't immediately figure out what it is. It is not 40. If you're thinking, okay, it just equals 40 because these will balance. No, that's not correct, because that would give you a net force of 0. 40 up, 40 down will give you a net force of 0. But mass times acceleration in this problem does not equal 0. M times A does not equal 0 because the A is not equal to 0. Mass will never be 0 in our class, but the A could be 0. So let's write Newton's second law and try to figure out what's missing. What's that missing force? And we do this in 9th grade. So you have seen it before. It just may have been a while. Okay, what this means is add up all the forces, and that arrow means you have to take direction into account. You can't just say up is the same as down, right's the same as left. You can't just say use positive numbers for everything. Well, in this problem, fortunately, we're only in one dimension, the vertical direction, the vertical dimension. So I can use positives and negatives. I'll call up positive and down negative. That way, this will be positive, normal force will be positive, and acceleration will be positive, but the gravity force will be negative. So this means write out all the forces, add up all the forces. So let's do that, because the forces are normal plus gravity. So the normal force is up, so I write it as a positive. Gravity, when people first teach this, I think it's not a bad idea to go like this. Add up all the forces. Add implies positive plus signs. So I'm going to write it that way. But gravity is down 40. And this is a vector equation, which means you can't just plug in a bunch of positive numbers for every force you see. For every single thing that has direction, you have to ask yourself, which direction does it point? How do I show that in the equation? Since this is only in one dimension, we're going to show up with positive and down with negative. So that means this is positive and that's positive, but this is negative. So to say plus gravity, I don't write plus 40, I write plus negative 40. That's what it means with a vector equation. You're adding the forces, this force plus that force, but this gravity force in this equation is negative 40, because that little thing there means you have to take direction into account. This equation is only true, this natural law is only true if we take direction into account when we look at force and acceleration. Okay, let's do the right-hand side. The mass is 4. Mass will never be 0 or negative in this course ever. But acceleration could be 0 or negative. So let's put in the number for the acceleration. This says up 5. How do you tell the equation up? Well, of course, with a plus. So plus 5. All right, so you get Fn minus 40 equals 20. And so that tells you the normal force strength has to be 60. So back up here, I write 60 newtons. Okay, it's possible to reason this out. So that's the way you would program a computer to do it. But it's perfectly okay to think, okay, let's see, my M times my A is 4 times 5. That's 20. So I need 20 extra newtons to make that happen. I need 20 newtons more in that direction than in the other direction. Okay, I've got 40 newtons down, so I need 20 newtons more than that up. I need 60 newtons. Or another way of thinking of it is I need to cancel out that entire 40 newtons plus add 20 more so that I can make this happen. So 40 plus 20 more is 60. The extra excess net leftover force of these two is 20 extra newtons to make this happen here, to make it 4 times 5. That's a perfectly legitimate kind of common sense, intuitive way of thinking about it. And if you're careful, that also works.